So what is this chi-squared random variable? So we could and we will answer that question, but in some sense, it's not really the only question of interest. Not just what is chi-squared, but why is chi-squared is equally important. But let's start with the what first. So as I said, the chi-squared random variable is an example of a gamma random variable. So this is the gamma random variable with alpha being n over 2 and beta being 2. So recall that the gamma variable, this is of course the Greek letter, and this is how we write it in English. The gamma variable is governed by the probability density function, which is given as, so I don't know, let's call it, f of x is 1 over beta to the alpha gamma of alpha times x to the alpha minus 1 e to the minus x over beta if x is positive, and it's 0 if x is less than or equal to 0. So this is the definition of a gamma random variable. And in particular, we're looking at the case where alpha is n over 2 and beta is 2. So you can just, plug those in and get what you get. That's the gamma random variable. So that's one kind of an answer. But that's not particularly that doesn't explain why this is coming up. So really we should say why is chi-squared m interesting, Wow. So it's one thing to know what the chi-square random variables are, but it's another thing to understand why they come up. So let's understand, why do these chi-squared random variables tend to arise? And the main point is that if you have a standard normal random variable and you square it, then miraculously you get a gamma random variable. And not just any gamma random variable, you get a chi-square random variable with 1 degree of freedom. So you get this nice special gamma random variable. And what that tells you, in addition, is that if z1 through, let's say, zn, let's say through zm, are identically distributed independent random variables, independent identically distributed random variables, standard normal, then, well, what happens if you take the sum of those zi squareds? Then this is a chi-square random variable with m degrees of freedom. All right, so there's one last thing to do, and that is, it's the fun part. It's to see why the chi-square distribution comes up when you're looking at the sample variance. So we're going to look at this very particular combination, n minus 1 times the sample variance divided by the variance of the population. And we're going to just kind of break this thing up and try to understand why this thing has a chi-square distribution. Okay, so I'm just going to algebra this thing, okay? So let's write this thing up. So what is s squared? Of course, s squared is the random variable, which is the sum of the xi's minus the sample mean squared divided by n minus 1. So this numerator here, because I'm multiplying by n minus 1, is really just the sum of the xi's minus x bars over sigma squared. Okay, and now if you squint at that a little bit, let me just pull these things out to make it easier to squint. Then what you can see is this thing, it kind of wants to feel a little bit like some sort of a normal distributed random variable. I mean, if you look at it, like this x bar, this mean, it looks kind of mu-like, doesn't it? And if that was a mu, then these would be just a bunch of like of of uh, normally distributed random variables. Okay, now that's not a mu, but we wish it were a mu. So let's make it a mu and just add and subtract, the usual trick. Okay, so this is just by way of trying to motivate this this stuff that we're going to do now. Okay. Oh, I'm sorry, my parentheses are on the wrong side. Okay, I meant to write that, of course. Okay, so sorry. Now this looks a little bit better. Okay. So yeah, I mean, I was just copying down this thing right there. Okay, so let's move along. So I want to try to squint and stick some mu's in here, but you can't. There's no free lunch, so we have to put the mu back in. You get something like that. Okay, so that's how I'm rewriting my top, and of course I'm still squaring it. Okay, now I'm going to go ahead and FOIL that top out, but I'll keep these terms clumped like I'm doing. So this is the summation. This is kind of off to the side here. I get the summation of xi minus mu squared. I get the cross terms, which is 2. So all this is inside the sum. 2 times xi minus mu times mu minus x bar. And then I get plus mu minus x bar squared. All that's divided by sigma. Okay. And now we have a sigma squared, I guess, because I just squared out the top. That's what I just did. Okay. This is a sum over, I equals 1 to n, by the way. Okay, so now I'm actually going to break this sum up over these 3 terms. So I get, on the one hand, my summation I equals 1 to n of my first bit, which is the xi's minus mu's squared over sigma squared. This is like a little bit of victory right there, because that looks like some normal random variables, right? Some standard normal variables. The next term is, so I have, if you look at this next term over here, you see this is just a constant. This is a constant, that's a constant. So that stuff's going to pull out of the sum. So we get a 2 times mu minus x bar over sigma squared times the sum, I equals 1 to n, of xi minus mu. Okay, and then my last term, so this is, I'll just clump these up together. And then my last term is a, so it's mu minus x bar. I'm going to write that in reverse order because I'm squaring it. So the order doesn't matter because that's just flipping the sign, and then I'm squaring it, so it doesn't matter. Okay, so this x bar minus mu squared over sigma squared. Okay, now this term in the middle, I can actually do this sum, right? So when you do this sum, the salient point here is that if you add up all these xi's, well, what do you get? If you add them up and divide by n, you get the sample mean. And so what that says is if I were just adding them up, I'd get n times the sample mean. And that is what part of this term looks like. If I break this sum up, then this first sum is n times the sample mean, and the second is just n times the mean. So let me go ahead and do that. Let me get this over. That's just side work. So this whole thing is, this first thing is a sum I equals 1 to n. Let me just pull this on the inside, just to make it a little more suggestive. Xi over sigma square, over sigma quantity squared. And now, as I said, we have 2 times, actually, you know what I'm going to do? Because I want the x to be on the left and the mu to be on the right there, I'm going to reverse the order of that term and change this to a minus sign. So I'm going to do minus, and then I have twice x bar minus mu. over sigma squared. So I just used switching this order to introduce this minus sign there. And then I add up those x's and I get n times x bar. I add up the mu's and I get n times mu. Okay, good. And then that's plus, and now again, I'll bring this all together. I get x bar minus mu over sigma quantity squared. Okay, let's keep going. You can feel it, right? You can feel it. I can feel it. We're getting there. We're getting close. We're on to something. So xi minus mu over sigma quantity squared minus, okay, now check it out. I can pull that in out front. And then what do I have left? I have left, so if I pull this in out front, I have an x bar minus mu, which is the same as I have there, which means I just have the thing squared, right? So this gives me a 2n over sigma squared, and then x bar, I don't know why I put it like that. Let me just write it a little bit different. I get a 2 n, and then I get an x bar minus mu squared over sigma squared. So like I've been doing, I'm gonna just put the square on the outside just for fun. Oh, I did that. Nobody caught me. Well, maybe you guys did catch me and you're wondering what happened, but you might have noticed that I lost my summation on that last term. I apologize, okay? I have this sum, I'm adding these three things together, and this sum would have been right there. The sum is supposed to be there. This is just a constant, right? So what happens when you take the sum of that constant n times, this thing should be multiplied by n. So I'll put that in red because that's like my mistake there. There's an n there, which is coming from that sum. And then there's an n over here. And then when I'm copying it down on the next line, I get an n times x bar minus mu over sigma squared. Okay, look, I have two n's, I take away an n, and what do I have? I have a sum I equals 1 to n of xi minus mu over sigma squared minus, I have minus two n's, and I'm adding one more n, so altogether I have minus n times x bar minus mu over sigma squared. And why don't I put that in on the inside and on the bottom and stick a square root on it so that it'll look more familiar. I get I equals 1 to m xi minus mu over sigma squared minus, and then I have x bar minus mu over sigma divided by square root of n. If you do the flippy square, then that'll come out as it is above. So this is great, right? These are standard normals. This is a standard normal. And all this is equal to what we started with, n minus 1 s squared over sigma squared. Okay, so now I have related my this particular variable of interest to some, well, actually a difference of some standard normal variables. So now, how do we finish this off? So we are going to use an assumption that is not justified. So I'll just try to be clear about that. But if I'm moving things over so that everything looks like sums, what this tells us is that n minus 1 s squared over sigma squared plus this x bar minus mu over sigma divided by root n squared is this sum I equals 1 to n of xi minus mu over sigma squared. Okay, now what does this tell us? So this is a, as we were saying, this is each one of these is a standard normal random variable. I'm adding up n of them, they're all independent. So this is a chi, chi square with n degrees of freedom random variable. This one is a single standard normal random variable squared. So this is a chi-square 1 standard normal random variable. And the question is, of course, what's this one? So to figure it out, I'm going to use moment generating functions, but to do that, I need to make an implicit assumption here. So if these are independent, then the moment generating function of the sum is going to be equal to the product of the moment generating functions. They are independent, but that requires a little bit of extra work, and I'm just going to skip that for now. Okay, so I'm just going to use the fact that they're independent, and what that tells me is that, so let's call this random variable over here that we're trying to figure out, I don't know, y. Okay, so we're trying to find y. And we know that the moment generating function for y, if I multiply that by the moment generating function for chi squared with 1 degree of freedom, then I get the moment generating function for chi squared with n degrees of freedom. You know, this is from the moment generating function of the sum is the product of the moment generating functions. Assuming independence, and we're going to assume that. Okay. And hey, guess what? We actually know what these moment generating functions are. So, you know, so because we know that these are gamma random variables, we know what those moment generating functions look like. This thing is 1 minus 2t to the minus n over 2. This thing is 1 minus 2t to the minus 1/2. This thing is a question mark. But look, you can just multiply it over and solve. So you got my of t is 1 minus 2t to the minus n minus 1 over 2. And that happens to be the same of the moment generating function for chi squared n minus 1. And because, you know, moment generating functions determine, that tells us that y has, you know, is a chi squared n minus 1 random variable. And of course, y was n minus 1 s squared over sigma squared. And that's what we wanted to show. Yay. Okay.